Chapter 9, Learn Smart, is going to complete this evening, so if you haven't finished that Learn Smart assignment, make sure you do that. I also want to mention, I don't know if you know or not, I think if you go to the Library tab in Connect, I think that's right, you can actually go back and go through the old assignments, old Learn Smart assignments again if you want. That's good review also. So if you weren't aware of that, and I think again, it's in that Library tab. You should be able to see all those again. So once you're done, that resource is still there for you. Let's see, what else did I want to mention? Yeah, I never got around to doing a problem set for Chapter 9. Sorry about that. I can see lots of complaints have come in to remind me, right? Probably for Chapter 10, we'll do another assignment. The Chapter 8 assignment, actually there were a fair number of questions on there for the Connect problems, not the Learn Smart, but the Connect problems. And I think I meant to assign all of that to like 5 points per question. I think it defaulted to 10 points per question. I'll probably scale everything and adjust it closer to the end of the semester. What I want is the homework to be a learning thing, not necessarily something that will hurt your grade. So I don't want it to hurt, but I want it to be learning. So it's there to encourage you to do the homework. But remember, overall in the end, all of the homework combined together is just going to factor 10% of your grade. So if you miss one question here or one question there on the homework, it's probably not going to be significant. But if you miss a lot, it could affect your grade. So just wanted to throw that out there. Okay. So I just want to reiterate some of the things we've been talking about this week in terms of alkynes. So if we think about alkyne chemistry, to make them and what we can do with them, the chemistry has a lot of similarities to things we've seen before. So one of the best ways to make alkynes is by doing elimination reactions. So we need to have leading groups in order to eliminate HBr or HCl with some base. Base being something like hydroxide, alkoxide, or amide base. But we have to do it twice, right? So if we're forming 2 pi bonds, then we have to do 2 eliminations. So you have to have 2 halides or 2 leading groups on there in order to do eliminations. And then alkynes, when we want to build up alkynes into larger alkynes, we can take advantage of the fact that alkynes have acidic hydrogens if they're on the end of a chain. And a strong enough base, not any base, but a base that's strong enough, like NaNH2, can deprotonate that. And once you have now a carbon with a minus charge, it's a good nucleophile. So you can do all the substitution chemistry that we can do with other kinds of nucleophiles with acetylides. And they're very good nucleophiles. Okay? We can reduce the pi bonds. We can do reduction of alkynes in 3 different ways depending on our desired outcome. Okay, so we can take an alkyne and reduce it with palladium catalysis with hydrogen gas. And that goes all the way and reduces both of the pi bonds all the way to the alkane. It's hard to control and hard to stop. If we poison that catalyst or reduce its reactivity with something we call Lindlar's catalyst, and that's really what you should remember. You won't have to regurgitate all of this stuff, but if hopefully you recognize Lindlar's catalyst as the poisoned, less reactive one, you should know that it stops after addition of 1 molecule of H2. And it does so to give a double bond, which is with the cis stereochemistry, because the 2 hydrogens are adding on the same side. All right? If you want the other stereochemistry, then you have to use a different mechanism, a different way to do that. And these alkali metals, these are neutral now with their electrons. So lithium or sodium has 1 electron in the neutral metal state. And that electron can be donated easily to an alkyne. And that can happen twice, and then overall you end up with the alkene, but in the trans configuration. And please note that ammonia here is only the solvent. It's the metal which is the important part, and so I've noticed in the past if I've asked what reagent you need to do this, people would just remember NH3 and put that. NH3 isn't going to do this reaction. It is really the metal giving up its electron, which is resulting in reducing those pi bonds and getting the CH bonds. Okay? So, and I mentioned this last night if you were at the review session, anytime we talk about all these different reactions and the details of them, you should become more and more familiar with the things that we're writing here in terms of the reagents and know their roles. Know what is a nucleophile, what is an electrophile, what is just a spectator solvent, and not necessarily spectator, but not something that's adding to your molecule, but is the solvent or not. So know the roles of the things that we write on these reaction arrows. The pi bonds in an alkyne are nucleophilic, they're electron rich, and they're looking for electrophiles, and those electrophiles could be H+. Those electrophiles could be a Br plus or Cl plus. Those electrophiles could be an H plus or catalyzed by mercury. It's really a mercury plus, which is helping that. But allowing then the addition of a plus and a minus, right? An electrophilic addition. So if you have something like hydrogen halide, you can control that by the stoichiometry of the reaction. So an alkyne plus one equivalent of HBr would give you addition of H and Br across the double bond. One of the pi bonds, leaving you a double bond with bromine. If you add a second one, or there's excess of that reagent, then you'll add twice, just like the chemistry of alkenes that we already know. Same thing with dihalides, Br2, Cl2, I2. Those will do very similar things, except now we're adding a Br plus and a Br minus, right? And just like everything else, it adds trans across the double bond, the triple bond, to give the double bond with the trans orientation. To add water with alkenes, we can just use H2O with an acid catalyst. But in this case, with alkynes, it works best to use, in addition to just acid, a mercuric sulfate to do that and help that addition. So it's actually an Hg in the 2+ oxidation state. That's interacting with the pi bond like a proton would in the normal addition to an alkene, similar. And then it allows the water to add in the second step. But the mercury doesn't hang out there. It's lost in the end. So the important thing to remember is that if you start with an alkyne, it's the water which is the thing that's adding. Overall, it's the equivalent of H plus and OH minus adding across one of the pi bonds. But then you have to remember that this product isn't stable. And it rearranges very quickly. The proton here ends up on this carbon, and then the double bond moves up to the oxygen. So that rearranges to shift that proton over from oxygen to carbon, and you end up with a ketone as the stable final product. All right? All of these take place with Markovnikov selectivity. For example, if I didn't have a terminal alkene here, or alkyne, but if this alkyne were at the end of a chain, you add H plus and Br minus, where does the Br go? To the more substituted side, just like normal. Okay? So that's important in the case when you have an alkyne at the end of a chain. Same thing with this hydration. It ends up with the plus adding to the least substituted side, that would then eventually be hydrogen, and OH to the most substituted side. Okay? What else can we do with alkynes? Other reactions of alkynes. We can oxidize them. So we talked about reductions of alkynes. We've talked about addition of electrophiles to alkynes. We can also do oxidation with ozone. So ozone, remember, breaks apart the carbon-carbon triple bond completely. And so for all three of those bonds that were between the carbons initially, those are replaced with bonds to oxygen. So in order to have 3 bonds to oxygen, you need to have, one of them is in a double bond form and one is in a single bond. Okay, and it breaks apart both sides. So whatever is on the left side, so here's 1, 2, 3 carbons, right? And that gives a 3-carbon carboxylic acid from that side. And then the other side, there's 2 carbons. So that gives a carboxylic acid with 2 carbons from the other side. All right. So depending on what all's on there, it's just going to break it apart, slice it apart, and oxidize the end all the way to carboxylic acid. This is similar to the chemistry we saw in chapter 6. So I want you to remember that for the last test, we didn't quite finish all the way through chapter 6, so we weren't stressing the chemistry that's at the end, from like section 6.19 on or so. But those reactions you should know also. Ozone reacts with double bonds as well to do exactly the same thing. It splits apart the double bond. But since these already have a hydrogen on them, right, that hydrogen is still not written here, but it's still there in the product. It's the two bonds break, and so we have to have two bonds to oxygen on either end. Question?
Yeah. So why was there OH added to with the triple bond and then not the?
Well, the OH, keep in mind that these reactions are done in water, aqueous conditions at the end. So that's where the oxygens are all coming from here, well, partly, and partly water. But the fact that you have three bonds, you have to have three bonds to oxygen, and the only way you can do that is to have two of them be to one oxygen and one being to one oxygen. So something else has to go eventually onto that oxygen, and that's the hydrogen. So it's not necessarily that it's an OH. Here, with two bonds, we break it apart, and we end up on either end with two bonds to oxygen. Okay? The most stable form being a CO double bond. So in this case, if it's an alkene, then we can have hydrogens there. Those hydrogens would be still on those carbons. So we haven't touched those. It's only touching the bonds between the carbons. That's the point of this. I showed you an example that has a cyclic alkene for a reason, because if that double bond is in a ring and you break it apart, the two ends are still connected. So the molecule, although it's no longer a ring, your two sides are still part of the same molecule. If that double bond were not in a ring, those two sides, those two things would be separate molecules, right? Just like in the top case, we break apart completely, we get two molecules. Okay, sometimes that ring thing messes people up, so I want to reiterate that. Another reaction we had with oxidation was this one, which takes a peroxide acid. MCPBA stands for this. Metachloroperbenzoic acid was the name of that. Which takes an oxygen and inserts it, adds it to a double bond, but does both bonds at once. So we end up with a functionality which we call, anybody remember what this is called? This functional group? An epoxide, right. Epoxide, a three-membered ring containing oxygen. That's an oxidation reaction too, because we replace CC bonds with CO bonds. So that's why I sort of classify all of these as oxidation reactions. Okay? So remember that. That was way back at the very end of chapter 6. Don't worry about the polymer chemistry and things like that from the end of chapter 6. I'm not going to cover that on the test. Let's see. Well, let's just take some examples of problems and go through them. So all this chemistry we've talked about, the things we can do with alkenes, the things we can do with alkyl halides, or tosylates, or alkynes, all of these reactions, we're now building up a toolbox of things that we can connect together in different ways to accomplish multi-step synthesis. And that's really the goal. The more you learn these things, the more you can think about how to connect them together to do things that you couldn't do necessarily in one step. So, although it's kind of fruitless to start from a starting material and get back to that in the end, kind of a waste, but it does illustrate some chemistry here. So if you were to see a problem like this, how would you start to approach what to fill in those boxes? Okay, I've left reagents out. I've left structures of products for reactions out. So the idea when we try to think about solving problems like this, or thinking about how to connect all this together, is thinking not just in a forward direction, but thinking in a backwards direction. Okay? So here I have an alkyl bromide, right? When you see that, you might think, well, what kinds of reactions do I know that could make an alkyl bromide with one bromine? Okay, what kinds of reactions are available to me that would allow me to do that? And then I know if I go from here to here, my goal is to somehow get to a molecule with two bromines, right? But you don't know a way to do that directly. That's why I've even shown you. If I just gave you a blank slate with none of these arrows and boxes, it'd be much harder. At least I've told you how many steps it takes, right? Well, let's think about this. In this molecule, we have the difference is there's a bromine in that position that did not exist in the original molecule. In the original molecule, it's just a CH2, right? It's not easy to do things with a CH2. What things do you know can put a bromine on a molecule? And particularly, what things do you know, what reactions do you know that could make a dibromide?
First off, you want to get rid of the bromine.
Well, what do you think I would have to start with here to get two bromines on a molecule?
You'd have to get an alkyne on that.
Not an alkyne. Not an alcohol. That would require two alcohols. Right, you could have an alcohol here and an alcohol here. But it's simpler than that. What's the one reaction you know that you could take something and get a dibromo product?
Bromination of an alkene.
Bromination of an alkene, exactly. So if you could see that this reaction requires an alkene, and you add Br2 to it, you can make that product. Okay? That's thinking backwards from that dibromo material. Now, there are a number of ways you can think, right? What possibilities could you think backwards? I heard alcohols, I heard this. But then the next question you have to ask is there a way to go from this thing I gave you at the beginning to that? So whatever you put here has to fit with that also. So you know how to take this alkyl bromide and make an alkene, right? What would you react it with?
Strong base.
A strong base. Elimination. Something like, well, I could use KOH, I could use sodium methoxide and methanol as the solvent, you know, something like that. Alkoxide. We talked about that when we talked about E2 eliminations. Right.
With the NaNH2
And NaNH2 would be a very strong base. You could use that too. So as we go along, even though the base NaNH2 wasn't introduced when we first talked about this elimination, now you know that base exists. All right? It's a strong base. It should work there also. And it does. So alkyl bromide, and I want two bromides. What I have to do is think about how to get some kind of reactive functionality here that allows me to put a bromine in. And that would require a double bond and then bromination. So you kind of see how you try to work in both directions in the thought process here. Okay, and I didn't really highlight it here, but let's just say we use KOH and heat, probably. And there's probably a lot of KOH, so I'll say excess KOH. Hopefully that gives you some hints as to what happens there. Yes?
An alkyne will be produced.
Yeah, that's right. We make an alkyne. So where the two bromines are, so that's a 3-carbon side chain. So between this carbon and this carbon, we make an alkyne. And then don't forget the methyl group on the end. Okay? Don't forget that. So that's elimination to make an alkyne. Now, I made this into a loop, this reaction process. We know that there's reactions we can do on alkynes, right? But are there reactions we know we can do in alkynes to get back to where we started from? overall, we've added from this alkyne to this, what things have been added to the molecule? What's been added? We just count the atoms, right? What's different from that to that? There's hydrogens and bromines. So overall, there's, so we've added 3 H's and 1 bromine. How do we do that? So there's lots of clues you can think about, right? You could HBr and 2 hydrogens left, H2. Right? Hopefully that tells you what these 2 steps must be. We need to first add hydrogen to get a double bond. So we want a double bond that we can then add HBr to. So this is HBr. This is hydrogen. But we need a catalyst for hydrogen. Right? You can do Lindlar's catalyst, that's right. Lindlar's. And Lindlar's catalyst specifically, depending on what you choose here, Lindlar's catalyst will give you the cis double bond, and then HBr will add to that. Okay? Another way you could reduce it, H2 with palladium on carbon would go too far. You can't use that. But this isn't the only possibility. You could use something like lithium in ammonia. The only difference is you'll end up with the trans double bond instead of the cis, but that doesn't matter. Okay. So when we think about multi-step synthesis like this, by the way, if you go on in 342, you're probably seeing a lot of problems with multi-step synthesis as you build up even more and more reactions. That's the kind of thought process to go about solving those kinds of things. Okay, well, let's take a look at some other problems. Here's some that I pulled from some of the old tests. For each pair of molecules below, A, B, C, D, there's 4 pairs of molecules. Circle the one that would be the best nucleophile. So now we're talking about being a nucleophile. What's the property of a nucleophile? How do you describe it, what a nucleophile is? Something that gives up its electrons easily. Now I have to qualify that. You're right, but it's not. It doesn't just throw away its electrons to something else. That's a redox reaction, reduction and oxidation. It's something that has electrons that can form a bond to something else with it. It can share them, give them up to share. So it forms a covalent bond with the electrons. That's different than just giving up electrons. Because we saw lithium metal can actually give up its electrons and transfer it to another molecule. That's a little different. So in the broadest sense, a nucleophile is something that has electrons and wants to give them up or share them with something else, with an electrophile. So if we look at each of these pairs of molecules in that broad context, you should hopefully not have a problem thinking about which one would more easily have or share electrons, right? So here we have BH3 and we have NH3. That should be a no-brainer, right? Which one's the better nucleophile? Better nucleophile. NH3, that has a lone pair. Oops, I gotta turn on the pen. That has a lone pair on the nitrogen. Borane only has 6 valence electrons. Oops, I shouldn't circle that. So that's the best nucleophile of comparing those two. Okay, so this is part of thinking about recognizing the reactive properties of a molecule. Of course, the reactive properties depend on what it's reacting with as well. If you take a look at B, we have cyclohexane and cyclohexene. Which one can more easily form bonds with its electrons? Yeah, the cyclohexene. That's the only one that can do reactions with electrophiles because we know now that the pair of electrons in the pi bond are available for doing reactions with. We can break that pi bond with reactions with a proton, add HBr, add Br2, or do oxidation. It's those electrons which are forming a bond to some electrophile. I'll just say E+. Alkanes don't do that. You're not just going to take a carbon-carbon single bond and give those electrons up to something else, right? But it is an it is a nucleophile. So when we talk about nucleophiles in the general sense, it's a nucleophile. Phenol, benzene ring with OH versus benzene ring with SH. Which would be a better nucleophile? Structurally very similar. Now we're talking something that's a little more close to what we've been discussing in the substitution chemistry chapter. They both have lone pairs. They both can behave as nucleophiles, but one of them is holding on to the electrons a little more loosely. Right? So it's going to be the sulfur. So remember, as you go down the periodic table, if you're comparing the same column of the periodic table, the ability to share electrons becomes easier as those electrons get further away from the nucleus and more spread out. They're held less tightly. And so that means they're also better at being a nucleophile and doing those reactions. And the last one, I have an enol form. Actually, we know that that's not stable like that, but it does exist. I summarize it to ketone. But if you compare the enol to an enolate, which one would be a better nucleophile? Yeah. The enolate, yes. If it's essentially the same structure, we're talking about the electrons on the same atoms, the one that's negatively charged will be more reactive or better than the one that's neutral. Okay, so any questions on nucleophilic properties? Other good nucleophiles? Well, just in general, when we talk about substitution chemistry, right? Nucleophiles such as cyanide, that's a good nucleophile. Azide's a good nucleophile. What else? We talked about acetylide, right? The anion of acetylene or an alkyne. Those are good nucleophiles. In general for SN2 chemistry. We have a bunch of others. Halides, actually the halides, iodide, bromide, even chloride. They can act as not only just leaving groups, but they can also act as nucleophiles. Again, going down the periodic table, the better the nucleophile. Poorer nucleophiles are things like hydroxide. Not that they can't be nucleophiles, or alkoxide. I'll just say R. Why do I say those are poor nucleophiles? They're pretty reactive reagents, right? Why are they poor nucleophiles? Poorer nucleophiles. They do something else a little better. They act as Bronsted bases. They're strong Bronsted bases. So they actually tend, if it's possible, to depronate rather than react at carbon. They prefer to depronate. So that's why those tend to favor elimination reactions as opposed to something like this. Okay. What else do I have here? Okay, rank the following molecules in order of reactivity for SN2 substitution. By the way, I believe this is from the 2004 or 2006 exam. You can find them all on the whole web pages. Rank the following molecules in order of reactivity for SN2. Okay, so what's important for substitution in the SN2 mechanism? Methyl primary or secondary are best, right. Tertiary is worse. Because the SN2 reaction is the one-step reaction. The leaving group is leaving at the same time the nucleophile is coming in. So the nucleophile has to come to the 180 degrees from the leaving group to form a bond in that transition state. That's the rate-determining step. So the least crowded it is, the faster or easier it is. Of course, the leaving group ability has something to do with that also. But the substitution is the most important. So methyl is going to be number one, most reactive. Primary, second most reactive. The secondary one here is the third most reactive, and the tertiary is going to be the least reactive. Okay, and same thing for SN1 substitution, which is going to be most reactive. The tertiary, right. Now we have methyl, that's going to be least reactive. In this book, we didn't really talk about the role of having double bonds adjacent. That actually helps to stabilize plus charges. We'll talk about that in the coming chapter, chapter 10. So actually that one is second and this one's third. But that we haven't discussed that yet. Okay, RNS. Is anyone still having a problem determining configuration, RNS configuration? There are a number of examples out there. Here's some. Let's take, for example, this Zoloft. Zoloft has 2 stereocenters. Let's take a look at this one and determine RNS. So you have to figure out the priorities, right? The lowest priority group, in many cases, is hydrogen, but if there's no hydrogen on the carbon, you have to think about that. In this case, hydrogen is going back, and we have 3 carbons, so which is highest priority? Yeah, this one that's in this more highly bonded is going to be priority number 1. Okay, so that group is priority number 1. Now we have 2 CH2s. You can't tell from that. So those 2 CH2s, we can't tell. We need to go out one more. Here's a carbon and here's a carbon. So if we go up and to the left, we get to a position where we have a carbon attached to nitrogen, and this carbon is attached only to other carbons. So this is going to, this direction up is going to be second priority. That's going to be third priority. Okay, that one's a little more, takes a little more thinking because it's not just, you can easily tell oxygen versus carbon, right? But here you have to go out a little bit further. So that's going to be the S configuration. Okay. Let's see, let's do this one on this AZT. Nitrogen, oxygen, carbon, hydrogen. Hopefully that should be easy, right? Which is highest priority? Oxygen, yes. Remember, oxygen is to the right, higher than nitrogen. 1, 2, 3, and 4 is going to the back. So that configuration is R. Good. If you still have trouble with that, I would recommend you practice that over the weekend, because you'll need to do it. Let me just go through these, a few of these. So in this problem, we're looking for the relationship between molecules. Okay. So if you have stereocenters, the number of stereocenters, it's important to recognize which stereocenters lead to what properties. This one, I just want to point out a couple of things here. Notice on this molecule, the carbon chain is in this zigzag orientation, and this one is not in, this one is rotated. So you can't just go by what the bold says. If you rotate this up, and this OH group over here would go in what direction? It'd go to the back. So this one actually has an opposite configuration there than there. The other one is the same. So two stereocenters, one is the same, one is opposite. What kind of relationship? They can't be mirror images. They're not the same. Oops. So it has to be diastereomer. We haven't changed any atoms, by the way. Constitutional isomers, I think, was a, I don't know if I have any up here. The second one, regardless of what the chlorine is, even if that is inverted or the same, notice I have a trans double bond and I have a cis double bond. Right away, they can't be mirror images or configurational diastereomers, but they are diastereomers because of the double bond. Okay, that one tricked a lot of people that year. That was a good one. I like the tricky problems. How about this one? Quick, yes, identical. There's a plane of symmetry, and you can see that that mirror image is identical, so those are the same. Is it the identical one? Here, we have mirror images, but now notice, these groups are not the same. There's no plane of symmetry in that molecule. They're mirror images, right? Enantiomers. And finally, the last one.
Constitutional.
Constitutional isomers, right. Notice, here I have substitution on 1 and 4. Here I have substitution on 1 and 3. I've actually moved an atom around. Regardless of what the configurations are, they're completely, there's bonding that's different. So they must be constitutional isomers. Okay, so I'd encourage you to go through the Learn Smarts. I'd encourage you to look at some of the old tests, and I want to finish today with a quiz because you knew it was coming, right? So we'll take a quiz today.